Welcome back to Lesson 2 on our Unit 3 covering the transport layer of the TCP/IP protocol model. The course is based on the text Computer Networking, a Top-Down Approach by Jim Carouse and Keith Ross. We've been discussing the basic issues of the transport protocol in Lesson 1, and we'll just pick up right where we left off. Now let's talk about extending the host-to-host delivery service provided by the network layer to a process-to-process delivery service for applications running on those hosts. That would be the transport layer. At the destination host, the transport layer receives segments from the network layer just below. The transport layer has responsibility of delivering that data in these segments to the appropriate application running on the host. Think about this for a minute. We've already learned that in this layered system of protocols, each layer is communicating with its counterpart on the other end of the network at that same layer. In other words, the web browser is communicating with the web server, a mail client is communicating with a mail server, and so on. In order to make that happen, each layer must rely on service from the layer below to implement the communication. This means that each lower layer is providing a service to the layer above. Now, we've talked about that quite a bit. TCP and UDP at the transport layer are serving Telnet, FTP, HTTP, SMTP, and so on at the application layer above, and relying on services itself from the network layer below. Suppose you are downloading web pages while running one FTP session and two Telnet sessions at the same time. You then have four network application processes running: two Telnets, one FTP, and one HTTP process. Remember, Telnet, FTP, and HTTP are all application layer protocols. When the transport layer in your computer receives data from the network layer below, it needs to direct the received data to one of these four processes at the application layer. First, recall that a process, as part of a network application, can have one or more sockets through which data passes from the network to the process and through which data passes from the process to the network. Therefore, as shown in this figure 3.2, the transport layer in the receiving host does not actually deliver data directly to the process, but instead to an intermediate socket. Because at any given time there can be more than one socket in the receiving host, each socket has a unique identifier. The format of the identifier depends on whether the socket is a UDP or a TCP socket. Now let's consider how a receiving host directs an incoming transport layer segment to the appropriate socket. Each transport layer segment has a set of fields in the header of the segment for this purpose. At the receiving end, the transport layer examines these fields to identify the receiving socket and then directs the segment to that socket. Do you remember from a previous lesson that TCP protocol uses three-way handshaking? That is, the sending and receiving hosts carry on a dialogue prior to anything being sent, where these sockets are established at each end. From that point on, each segment contains a field in its header with the appropriate socket to which the segment must be directed. This job of delivering the data in the transport layer segment to the correct socket is called demultiplexing. The job of gathering data chunks at the source host from different sockets, encapsulating each data chunk with a header information that will later be used in demultiplexing, to create segments and passing segments to the network layer is called multiplexing. Notice that the transport layer in the middle host in figure 3.2, there it is right there, must demultiplex segments arriving from the network layer below to either process 1 or process 2 above. This is done by directing the arriving segment's data to the corresponding process's socket. The transport layer in the middle host must also gather outgoing data from these sockets, form transport layer segments, and pass these segments down to the network layer. Although we have introduced multiplexing and demultiplexing in the context of the Internet Transport Protocols, it is important to realize that they are concerns whenever a single protocol at one layer is used by multiple protocols at the next higher layer. Now that we understand the roles of the transport layer multiplexing and demultiplexing, let's examine how it's actually done in a host. From that last discussion, we know that the transport layer multiplexing requires that sockets have unique identifiers and that each segment have special fields that indicate the socket to which the segment is to be delivered. These special fields, illustrated here in 3.3, are the source port number field and the destination port number field. Each port number is a 16-bit number ranging from 0 to 65,535. The port numbers ranging from 0 to 1023 are called well-known port numbers and are restricted, which means they are reserved for use by well-known application protocols such as HTTP, which uses port 80, and FTP, which uses ports 21 and 20. When we develop a new application, we must assign the application a port number. It should now be clear that the transport layer could implement the demultiplexing service. Each socket in the host could be assigned a port number. And when a segment arrives at the host, the transport layer examines the destination port number in the segment and directs the segment to the corresponding socket. The segment's data then passes through the socket into the attached process. This is basically how UDP does it. However, we will also see that multiplexing, demultiplexing, and TCP is yet more subtle. Recall from the last unit that the Python program running in a host can create a UDP socket with a client socket command. Client socket, one word. When a UDP socket is created in this manner, the transport layer automatically assigns a port number to the socket. The transport layer assigns a port number in the range of 1024 to 65535 that is currently not being used by any other UDP port in the host. Alternatively, we can add a line into our Python program after we create the socket to associate a specific port number to this UDP socket via the socket bind, open paren, close paren method. Bind, B-I-N-D, open parentheses, close parentheses. Typically, a client side of the application lets the transport layer automatically assign the port number, whereas the server side of the application assigns a specific port number. With port numbers assigned to UDP sockets, we can now precisely describe UDP multiplexing and demultiplexing. Suppose a process in host A with UDP port 19157 wants to send a chunk of application data to the process with UDP port 46428 in host B. The transport layer in host A creates a transport layer segment that includes the application data, the source port number 19157, the destination port number 46428, and two other values which we'll talk about later. The transport layer then passes the resulting segment to the network layer. The network layer encapsulates the segment in an IP datagram and makes a best effort attempt to deliver the segment to the receiving host. If the segment arrives at the receiving host B, the transport layer at the receiving host examines the destination port number in the segment 46428 and delivers the segment to its socket identified by that port 46428. Note that host B could be running multiple processes, each with its own UDP socket and associated port number. As UDP segments arrive from the network, host B directs or demultiplexes each segment to the appropriate socket by examining the segment's destination port number. It's important to note that a UDP socket is fully identified by fields consisting of a destination IP address and a destination port number. As a consequence, if two UDP segments have different source IP addresses and/or source port numbers, but have the same destination IP address and destination port number, then the two segments will be directed to the same destination process via the same destination socket, as you can see in this image coming up. Alright, you have the two sockets there on P3 and P4, 9157 and 5775. We have a socket 6428 on P1. Message comes from source is 9157, that's that port number on P3, and it's destined for port 6428, which is that port number on P1. P1 responds from 6428 to 9157. Understand that there could be multiple applications at both of these hosts. P1 sends a message out its port 6428 to P4's 5775, and then P4 responds. Okay, that is plenty for this lesson. Let's pause right here, take a break, take care of any business that you have to take care of, any assignments that you have waiting on you. And when you are prepared to move to lesson 3, come on back.